So fusion in the universe. We won't get into too much plasma physics here, but fusion is why you're here. Fusion is why you live. Fusion is the reason for all of life, for all heat and light on Earth. Fusion is the power at the center of the sun and stars, where at their center, at the center of our sun, for example, with a size, an overall volume, is a gigantic bubble of hydrogen. The size of the sun is about 300 times that, the mass is about 300,000 times that of Earth. So at the center of the sun, the hydrogen, the fusion that is going on, the hydrogen is about 70 times the density of steel. So these particles, which would naturally both be positively charged and push apart from each other, will actually be forced by gravitation. So that's how fusion works in the universe. Like fission, it involves the famous Einstein E=mc² equation, in the sense that a tiny bit of matter is converted to a massive amount of energy. But in fact, the fusion reaction is even more powerful than fission. So how do we do that on Earth, where we cannot do the same thing that is replicated in the sun? We don't have that gravitation. We cannot fake gravitation by building it into a small, a device that would, say, be big enough to power a city, into a fusion plant. So how do we do that? You see in the reaction here that we take these two elements of hydrogen, or two isotopes of hydrogen. If you see the orange balls, those represent a proton. Normally, hydrogen is just a proton. But when you add a neutron, the gray ball, it becomes deuterium. That's the far piece. And when you add 2, that becomes tritium. And you may not know these units, but 7 mega electron volts is their entering energy. This is what we get them to in the fusion reaction. And you see that following the fusion reaction, you get two products. One is essentially helium. That's a helium nucleus. It's non-radioactive, but if you see the units, it's 5 times more powerful than the incoming value. So that's where you've gained the energy. In addition, you look at the neutron that is produced, it's 14.1 mega electron volts. To compare, if you release that neutron in free space, it would reach the moon in 8 or 9 seconds. That is how insanely powerful that neutron is. So the neutron will collide with the metal walls of the fusion vessel, of the tokamak, the fusion vacuum vessel, and like a bullet hitting a metal wall, if you would feel that, the bullet would fuse and you would feel heat. That's essentially what the neutron does. It transfers its kinetic energy to the wall as heat, and the water circulating behind will then be able to make steam, and in a commercial plant to drive electricity. So that's deuterium and tritium that become helium plus energy in the form of the energetic neutron. What it requires to do this on Earth is that we have a very, very precise magnetic field. And I'll describe that in a little bit. But to get to these energies, we are actually going to, you'll see, 150 million degrees Celsius. The outcome is what we call a burning plasma. That is the goal of ITER. You'll hear me talk about it in a minute. But to look at the particles here, if you see the helium nucleus that has all that energy can still bang into the other particles. It can still energize the plasma, transfer its energy to the plasma, and continue to the point where the plasma, if you have enough of these reactions, the plasma becomes burning or self-heating. And that is what we're trying to do with the size of the ITER reactor. But before I get into the details of ITER, let me talk about where it came from. So this story is fairly famous. You may have heard it, but if not, in November of 1985, you see those gentlemen, Reagan and Gorbachev. That was the Geneva summit, where actually they were focusing on how do we reduce our weapons arsenals, our nuclear weapons arsenals, but they wanted, in addition, an initiative for peace. And this is where ITER came up with as something that would be a benefit for the benefit of all humankind. So quite rapidly after this was at the time of the Soviet Union still, but it started with the US and the Soviet Union. Japan and Europe joined quite quickly thereafter. And it went through a decade and a half of design, of engineering design, conceptual design, engineering design in different locations. Eventually, in the early 2000s, the question came, where will this be sited? Where will it be located? And the decision was eventually reached to place it here in France, where the ITER project is today, but with the participation of all the members. And of course, everybody would have liked to have had, every member would have liked to have had this location with the ITER project on their soil. And in fact, by this time in the early 2000s, you had Korea joining, you had China joining, in 2005, India joining. And so by November 2006, there you have the photograph of Jacques Chirac at the Élysée Palace. And that was really the signing of the ITER agreement. By August 2010, you see there at the bottom left, you have the fields being cleared. And today, this is the ITER site as we see it. And we're going to take you inside some of those buildings to see what it was, how it's really come to fruition. But the key here is that this is really a generational challenge. Why? Because what we today, as adults, have inherited from the previous generations and from our own consumption of energy using fossil fuels is a very negative legacy to pass on to our children. So all of these countries, and you can see the names here, China, EU, India, we talk sometimes, you see headlines about trade wars or about other disagreements, even border disputes, many things that go on between these countries. They're the most powerful countries in the world, and yet they are all united here, working side by side, hand in hand in a common cause. Why? Because our generational challenge is to leave a better energy legacy to our children and their children and the generations that follow. So how is ITER going to do that? We can describe the ITER mission in three ways. One is the phrase that you will sometimes see on our website and so forth. ITER is designed to demonstrate the scientific and technological feasibility of fusion power for peaceful purposes at industrial scale, to show that it can be done at size. There have been hundreds of tokamaks built that are smaller. This is the first that will be at the scale that is industrial scale. So we'll talk about why that's so important to all of these countries. The second one I mentioned is the burning plasma or self-sustaining plasma. And to do that, we can reduce the ITER mission to a single letter, Q. Q is the ratio of the output power, the thermal power generated by the fusion action in the plasma versus the heating power that comes in. Why is that important? Because it is a different plasma physics phenomena. Nobody has ever been able to study a burning plasma unless you can count the microseconds of in an H-bomb or being able to study remotely somehow inside a sun, inside a star. So ITER, as an experimental device, is intended to allow scientists to study that burning plasma. For that, we have selected a design that is a Q of greater than or equal to 10 in pulses, or a steady state that would be greater than or equal to 5. Why did we select that? We could have gone bigger, but since ITER is designed as an experimental device, which will go up and go down in power, there would be no point in designing a bigger facility. In fact, it's possible that over time, with stronger magnets, with other things, we will be able to construct smaller machines. We'll see how that goes. That's still in the future. However, the Q that we selected would guarantee that we would have a burning plasma and be able to study that phenomenon. That is why all of these countries are coming together and putting their resources into building the ITER device.